Pluto, the enigmatic dwarf planet residing at the outer reaches of our solar system, is stirring up excitement within the astronomical community. Recent reports hint at a possible encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this celestial clash. But how did Pluto end up on a collision course with its distant neighbor? And what might this cosmic collision mean for us here on Earth? Let's explore this unfolding event. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its unique orbit. Despite this change, it continues to captivate and engage astronomers. Recent predictions from prominent scientists highlight a worrying proximity between Pluto's path and that of Neptune. These experts caution against a potential collision between the two planets, posing a significant threat to Earth. Pluto's journey around the Sun is marked by its unparalleled characteristics within our solar system. Its orbit spans an extensive 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a departure from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One notable aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational influences exerted by other planets. The examination of Pluto's orbit commenced shortly after its discovery, presenting a puzzling trajectory for astronomers. Unlike the majority of planets, whose orbits align relatively close to the ecliptic plane, Pluto's distinctive features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these intricacies serves as evidence of the complexities inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem elucidates the intricate interplay of their paths and gravitational pulls. Terms like azimuthal libration, latitude libration, and the VZK oscillation contribute to unraveling this celestial puzzle. Astrophysicists assert that the azimuthal libration, responsible for maintaining planets in their orbits, plays a vital role in the context of Pluto and Neptune. This term signifies that when Pluto intersects Neptune's orbit, it is positioned at least 90 degrees away from Neptune, crucially preventing potential collisions. Latitude libration ensures that when Pluto approaches Neptune or other giant planets, it is situated significantly above their orbital plane, providing an additional layer of protection against collisions. The VZK oscillation explains why Pluto's orbit around the Sun appears unusual but remains smooth over time. Despite apparent randomness in space, numerical simulations in the late 1980s revealed that, despite stable properties, Pluto's orbit is technically chaotic, with minor initial deviations leading to significant differences over millions of years. However, Pluto's unique orbit maintains stability over incredibly long timescales, keeping chaos in check. Recent computer tests have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, significantly contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a substantial influence, while Saturn's impact, though smaller, also plays a role. Through comprehensive tests, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are essential for maintaining the order and predictability of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater chaos and unpredictability, potentially leading to collisions or ejections from stable paths, causing ripple effects on other celestial bodies. Understanding Pluto's orbit is particularly crucial amid discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the solar system. Pluto's case highlights how seemingly unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Continuous observation and study of these phenomena are vital for gaining a better grasp of our position in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The concept of orbital chaos vividly illustrates the sensitive dependence of a celestial body's path on its initial conditions. As demonstrated in Pluto's case, even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computer simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments in these simulations, astronomers can observe how minor tweaks can have a substantial impact on Pluto's trajectory. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's path. Despite features like azimuthal and latitude libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a tiny initial difference in Pluto's position or velocity can lead to significant changes in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable for an exceptionally long time, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Predicting cosmic events, especially with planets like Pluto that have unpredictable orbits, is quite challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limits of our predictive abilities. These models heavily depend on accurate initial conditions and simulate complex interactions. Even a small error can lead to significantly different outcomes, making precise predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can affect the stability and trajectory of other bodies in the system. Despite these complex forces, major astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a collision, which seems unlikely given these intricate dynamics, is now a topic of concern. Neil deGrasse Tyson, a well-known astrophysicist, offers a special viewpoint on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet instead of a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is always evolving. Tyson sees Pluto's reclassification not as a demotion but as a necessary adjustment to our increasing knowledge about the various objects circling the Sun. His approach to celestial mechanics involves continual learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes that the allure of these unknowns is what makes astronomy so captivating. Additionally, Tyson is aware of how space-related events and discoveries shape public interest in astronomy. He thinks occurrences like Pluto's reclassification and its unusual orbit are opportunities to capture the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes counterintuitive aspects of space mechanics, Tyson aims to foster a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other scientists, Tyson actively cautions the public about the potential danger of Pluto's unpredictable path. After extensive study of Pluto, he has raised concerns that the three-body problem might pose a real threat, suggesting that a collision with Neptune is long overdue. Additionally, Tyson emphasizes how such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. A collision between Pluto and Neptune would be an unusual and catastrophic event in our solar system. This collision would release a massive amount of energy, likely breaking apart Pluto due to its smaller size and icy composition. Debris from the collision could scatter across the solar system, posing potential hazards for other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a well-known theoretical physicist recognized for his work in string theory and science popularization, offers a unique perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can assist in navigating the solar system more effectively, predicting potential hazards, and planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a blueprint for approaching and understanding distant worlds. In discussing the physics of planets, Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are linked to fundamental principles of physics. Kaku's work in theoretical physics, especially in string theory, aims to comprehend these principles at the most fundamental level. He suggests that studying the complexities of celestial mechanics, like the orbit of Pluto, can yield insights into the underlying laws of the universe. Similar to Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astrophysics, offering a unique observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework replacing point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The collision of such magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme conditions, a key focus in string theory. Additionally, the gravitational wave produced by the collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a remarkable example of celestial mechanics, showcasing both stability and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. The universe holds many mysteries, and the three-body problem is just one of them. There are other potential disasters that scientists anticipate. While the chances of planets colliding in space are extremely low, it's not entirely impossible. The way planets' orbits are influenced by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1 with 7 Earth-sized planets, the gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently happening. Scientists closely monitor these systems to understand how planets influence each other's paths, particularly when they are near. This knowledge helps us comprehend the movement of planets in space. Rogue planets, floating through space without orbiting a star, introduce an additional unpredictable factor. These planets, formerly part of a star system, are expelled due to gravitational disturbances or other celestial events, such as the close passage of another star or dynamic instability in multiple systems. Over time, these wandering planets can traverse vast distances, potentially reaching regions far from their origin. During their solitary journey, there is a possibility of them intersecting with other star systems. If one of these nomadic planets enters another solar system, there is a slight chance of a collision with a planet in that system. However, Given the immense and predominantly empty nature of space, the likelihood of a rogue planet directly impacting another planet is very low. The vast interstellar distances and the scarcity of planets in open space serve as deterrents against frequent collisions. Additionally, rogue planets are relatively uncommon compared to the number of stars and planets in stable orbits, making such encounters even more improbable.